All right, so today we're going to talk about Lab 4, which is the next step of things. It's a pretty long lab, so I actually split it into two parts. The first part is going to build on what we did before with dplyr for data cleaning, and the second part is going to talk about tidyr, which is another tidyverse package. So I'm going to go ahead and share my screen here, and I will start to walk us through. So as before, I have RStudio open, and I have Google Classroom open. Where did it go? There it is. Before we get too far into that, we want to open our project. Not everyone likes to use projects, and in fact, it's one of the things Dr. Thatcher and I argue about. But if you do have a project open, it's actually a pretty nice, easy thing to do. You can see there I had a shortcut, so you can actually put a shortcut on your desktop, which I think would persist, which would make it easier to get to it. And you can see here are all of our previous assignments. And in particular, I want to point out that clean Kim data is living in this folder. If it's not living here, you're going to actually have some problems. So now I'm going to open up a new R Markdown file. Oops. And we can name it whatever for now. And then I'm going to get here into our Lab 4 and 4A I'm going to do in this first video. And it opens up like that, and then I can copy and paste it in. You also could get it off of the U drive, or I think I have it attached to the Google Classroom some other way. All right, so now I'm going to select all here, and I'm going to copy and paste it there. I'm going to make this wide because this is what we're going to be using. Okay, so let's go back up to the top. Again, change the date, change the author to be you. We haven't talked much about YAML code, but that's a thing you might want to do. All right, so this first chunk here in line 25, it's going to be loading the data in. I'm actually going to use read.csv. You remember read.csv is the one in base R. Read_CSV is the one that uses the readr package from tidyverse. One reason why we do like read.csv for files like this is that all the spaces that are in the longer variable names, remember shoe size was one we looked at last time, it'll be shoe.size, and then you won't have to do those funky back quotes. Anyway, if you do have the file directory here correctly, when you click this run current chunk, it should work just fine, and you see that Kim data is right here. In fact, that remembered that from before, so let's clean that out. So I just hit that little broom which deleted everything, but now I'm going to run it again and load Kim data into here. And you notice I loaded Kim data, and then I immediately renamed it Kim data working so that our original will stay nice and clean. I also tend to change the name. So instead of calling it clean Kim data, which is what the file name is, I gave it a different name so that we're unlikely to save over it on the U drive. Now, if you got a funky error at this point, that means that you're not in the right directory. So I would recommend opening up your project, or it could mean that you didn't put your file here last time. So if that's the case, you'll want to find it again. And again, you could use import data set. You could also just go out to the file menu and drag it to where you need to put it. But there are ways to do it inside R. Now, there is sort of this question, especially when you're getting data from the internet. Is it better to put a copy on your own machine, or is it better to download it from the internet? Now, some data is updated every day. For instance, if you want stock price data, every day that gets updated, or sometimes even every hour, every minute, but R, right, freezes it. So if you download it to your own machine, then you're only going to have that version. So getting it fresh from the internet every time you use it would actually be sort of cool for data where that's important. There's also a certain safety for your own peace of mind of having the data on your own machine, because if you lose your internet connection, you would lose access to your data. So you could imagine you're going to be working at the airport, or you're going to be taking the train somewhere, and while some trains and airports do have internet, it's often pretty slow or pretty pricey. So having the data set actually on your laptop would make that a little bit more flexible. Of course, data security is an issue, so having data on your laptop could compromise it, and sometimes sources will want you to keep the data on that central server rather than getting a copy for your own use. So, you know, it's sort of a give or take what you want to do. In this case, putting it into our project file will make it a lot easier for us to run. And if not, you could put wherever the actual path name is into here, u:// whatever. But you do want to get that. So if that gave you an error, you want to pause the video right now and go and figure out where your data came from and how you're going to work with it. All right, so you're back. That's good. File management is actually one of the trickier things we do, not just in data science, but in coding more generally. So if you ask your friend, the CS major, about file management, they're probably going to tell you how horrible it is and maybe use a bad word or something. And maybe you're at the point where you're going to say, man, coding sucks, or use a bad word of your own. And while that's maybe a good solution, it is true that it's just a problem and it's a thing that we got to figure out. And this is going to get worse when you're thinking about actual big data. If your data has 20 million rows, then every time you download it, every time you move it, it's going to take a few minutes to do, unless you're working on some kind of supercomputer. And so you do want to do that. And in fact, in some of the data science things that we do, like we do a contest called DataFest, when you do that contest, the first thing you do is you download the data set and then you subset it. So you do all of your initial analysis on a much smaller chunk of the data so that you can figure things out in a quick way rather than having to wait 5 minutes or 10 minutes or an hour for each of your analyses to run. As we get later in the semester, you'll see some of the cool modeling techniques we do actually do take a fair bit of time to run. That said, they're way faster than when I learned them back in the 90s. I used to do a mathematical model that I used in graduate school, and I would literally start it as I went home at the end of the day, hoping that it would be finished as I came in the next morning. There were others that were shorter, maybe 10-minute ones, so you could imagine you run it and then you would go get a cup of coffee or go to the bathroom or go visit your buddy or whatever, and hope that it was done by the time that you get back. So anyway, file management is annoying, and I'd like to say there's some magic solution, or when you get farther along, it gets easier, but it turns out it's just frustrating to make sure your data is in the right place. And even this idea of data cleaning that we're talking about is a way to try to make file management what you want it to be and to make the data so that we can actually do statistics on it. Okay, so we've now run all of those things there. So the next thing you might want to do is just go ahead and look at this file in Excel. Depending on if you watch the video, you may have already done that, but you'll see that there are some problems in this data set, and you could use the view command or one of the other ones to check that out. But even just looking here at the names file, you want to make sure you have your names here. Remember, we used read.csv, which made all of these longer variable names just have dots. So on dot off campus, dog dot versus dot cat, birth dot order. So that part at least is clean. And then you can use the view command, or you can even just click on the data set and it makes a little window here. So you can check that out. And you guys, I think, have already gotten a chance to play with this data set a little bit, and you notice that there were some misspellings in the way dog was spelled. There we go, CST, and a couple of other ones there. And a few of the things that are like that. So shoe size is the one I want to talk about. And here, you might think that, gosh, let's check out shoe size. Let's make a box plot. And that would certainly be a reasonable thing for us to do. And you go ahead and you make your box plot, and here it is. And what you see is it's a very skinny, not a box plot, a bar chart. Histogram, what am I talking about? It's a histogram. And when you do that, you can see that that outlier really shows up. Box plot, it's a bar chart. Box plot was the other one I had here, and in fact, you could make that one as well. And all right, I'm not going to mess with that because it's having some problems right now. All right, so anyway, back to our histogram. Anyway, it's funky, and it's funky because of this single point that is simply wrong. And I know the other command I was going to get, not box plot. I was going to just do a summary of Kim data working, $ shoe size, right? And if you run that summary, you can see that here's our mean and our median, right about 9, 9.5. The third quartile is 10.5, and then this crazy 113 size shoe. And you can make lots of decisions about what to do with that. At certain points, depending what I'm doing, I might have decided that that was a size 13 shoe because 13 is a size that exists. And it's easy to imagine somebody kind of double hitting the 1. you could imagine it's a size 11 shoe. But in any case, we got to do something with that. So using the filter command, which we learned before when we were learning dplyr, is the trick. So the line we put down here, and again, we piped this all to just be a single line, is to select shoe size and filter the shoe size greater than 50. And if we do that, you can just see there's only one entry. So what we did was we just took the data set, we selected that variable, and we filtered all the ones that were bigger than 50. So it's the only one bigger than 50. And you might say, well, gosh, why pick 50? And I did just pick it kind of randomly. If you want to make it 20, knock yourself out, and then you'll see it's still the only one over there. If you go much lower, of course, there are people who, size 15. There were a couple of those, I guess just one, a 16. So we're just using dplyr here in order to identify these really high values. And, with a data set this size, you could probably imagine yourself scrolling through, just looking at it or opening up in Excel. But if you did have 20 million rows, a technique like filter and select will help you do that. I also like this command for where we are right now in coding, because remember, select picks a variable, filter picks observations. And so using the two of them together, we were able to very quickly find literally that single data point that we were looking for. So we could find that. You could also look for missing values in NAs and see if there's something that you have. So we could do that. Here we'll also look for NA. So here again, I built kind of a pipe chain all in one row to group by the number of NAs, and it'll count how many there are. And you can see there's one NA value. So missing one shoe size out of whatever 377 observations is actually pretty okay. All right, so now we want to fix the shoe size that's wacky. And again, you could throw it out, you could change it, you could do whatever. And so I'm going to use this command here called if-else. And if-else can run as a straight command naked, or it can run inside of a dplyr pipe chain. So here in this first time, I'm just going to make this little fake data set here, and then I'm going to just use the if-else command. So there you go. So shoe size had these 5 values in it, and then I displayed it, and now I'm if-elsing it to just take out any of the ones bigger than 100. Okay, so now I'm going to build it inside of a mutate command inside of a pipe chain so that we can go ahead and work with it. So again, this is sort of a silly example, but this is exactly the sort of thing you're going to want to do. So if-else is a command, much like if in Excel. The command is if-else, and then it has a statement of if something is true, and then if that statement is true, the thing after the first comma is what you're going to assign this mutate to be, and if not, you're going to assign it to the second thing. So if shoe size is bigger than 100, we're going to make it NA. If not, we're going to keep it to be the value that it is. So here we are. Again, we're in the working file now. Kim data is still pristine and clean, and not clean, it's raw. And so here we go, we run it. Now you can see there's nothing here going on. And here I am going to make another histogram looking at shoe size. And you'll see that now I've now taken out 2 rows because there are now 2 NAs. The one up above had it there. All right, so here we go. Here is our new values, our new histogram showing the values for shoe size. Now, if I were to say, hey, is this a normally distributed variable? You go, oh, kind of, but there's these funky uppy downy things going on here. And again, the logic here is not that you're an expert in statistics, it's that you're an expert in shoe sizes, because we would use our content knowledge to say, hey, most people don't report a half size of shoe. So by asking the bins to be half a shoe size wide, what we've done is we've gotten half sizes, and those handful of people who do report half size shoes are now in these little lines in between. We could change that by making them whole values. And if we do that now, I would say we have a pretty normally distributed thing. Okay, so that's sort of a cool thing that we can do here. All right, so as before, the lab has some questions for you to answer. So go ahead and work through those. If you want to pause it right now and do that, that would be fine. Otherwise, you can wait. So notice that it asks you to do a couple of those things. All right, now I mentioned else if. The similar command that's slightly different and slightly more powerful is called case when. And case when is just if else for when you have a whole bunch of situations. So again, here is just a quick bar chart of dog, cat, and when you do it, what you can see is the most common answer was dog, the second most common answer was both, the third most common answer was cat, and the fourth most was neither, which is good because those are the 4 categories in the survey. But now you can see there are 3 more responses that they're really skinny, they actually only have 1 response. One person wrote car, one person was recorded as CST, and one person was recorded as DPG. I don't think it's too much of a stretch to suggest that those are typos. So we can use the case-when command to go ahead and fix multiple corrections like that. You could also use the table command to just get a table of all the responses with counts in order to do that. All right, so here we go. Here's again a small example I just made, just these 6 points. And then case-when is set up like this, and you put in each value, and then you put in what you want it to be. So case-when dog v cat is equals, because again, we're looking for when that's the case. So when that variable value is DPG, we're going to assign to it using the tilde dog. DPG is also going to, oh, that's just the same thing there twice. Now, here's the crazy thing is that you have to list every single value. If you don't, it's going to assign NAs to all the other ones. There's a way around that using an option called true. And so you go true is assigned to be whatever, and that'll assign all the other values to be whatever they were. All right, so anyway, here's a small example here, but now we're going to go back to our bigger example. And again, we're going to take Kim data working is assigned to be Kim data working, and then we pipe, and now we do mutate dog versus cat is equal to case-when each of these values goes along here. And we're just going to go down the line. And again, I've listed every possible. You could just do the typos and then do that true equals the original value. But for 6, it's just as easy to list them all. And as you do that, now you get your histogram where it only has the 4 values. Now, keeping this as a clear mutate command means that somebody else could come through and say, well, I'm not sure that's how you would recode it. Maybe somebody does mean they like cars better than cats. That's a different question than the one we asked, but that's certainly something you could imagine. And you could imagine more complicated cases where that would be the case. What's nice about case-when as opposed to else if is that you can do a whole bunch of them right there in a row. When you're just fixing one value, else if works pretty well. Else if also works well when you have not just equality, but you want to do greater than or less than numerical data. So some people would say you should use else if with numerical data and case-when with categorical data, but it's really several options available for that. All right, so the next thing we can do here is just look at a few more ways to make some graphs. The one I want to show right here is a geom, which is called geom count. And so what we're going to do is we're going to make the bar chart, which is here, and that looks like what we made before of who likes which of the different dogs, the different animals, dog or cat or both. And then here is a dot plot where what it did was it made the size of the dot equal to the number. And you can see here again that count dogs is the biggest and both is second and cat is a little smaller. And here we are comparing them by the gender. And so geom count is just a command that counts up the number of things to do that. So that's one idea for doing it. And again, you can see a couple other ideas for how to do that. Geom bin 2D is actually another cool one that makes this heat map where you can put the darker colors to mean things. So there's tons of geoms. I mentioned the cheat sheet. Again, I always keep one right near my desk so that I can look up a variety of different things. Google is your friend as well. So here's a 4th question, and it asks you to kind of interpret that graph, because if you haven't used a heat map before, it is a little bit tricky of a graph to do. So that's part A of lab 4, and I'll be back on the other video to do 4B, which uses tidyr to do a little bit fancier data cleaning.